let's get slowly ready for the last talk of today. Okay, so it's my big pleasure to have Professor Arnaud Triay from LMU Munich here, and he is going to talk about the free energy of dilute Bose gases at positive temperatures. So, Arnaud, we're looking forward to that.
So thanks for the introduction. Can you hear me well? Or? So first of all, thanks a lot to the organizers, the local ones, the semi-local ones, and the extra local ones. It's a very big pleasure to be here, and in particular to be part of the celebration of Volker's 60th birthday. So happy birthday again. Thank you to you all for staying. I know it's the last talk of today, so you're a bit tired, and I won't take it personally if you fall asleep. So if you have any question, just ask. I mean, I don't have so many slides, and your goal will be to ask me as many questions as you want so that I don't finish the slides. So I'm going to talk about the free energy of dilute Bose gases at positive temperature. So I also apologize for people who already saw this talk, but actually it's a revised version. So usually, normally I talk about the lower bound, but this time I will talk about the upper bound because I have a more educated audience in terms of QED or Fock space methods and so. This is a joint work with all of these people. So they are gathered up by institutions. So from the Copenhagen University or the extended Copenhagen group. So in particular, this is joint work with Søren Fournet, but also Lucas Junge, who is a PhD student of Søren, as well as Léo Morin and Marco Olivieri and Gerardo Teotim, who is at GSSI right now. It's also joint work with Christian Hansel, with Florian Haberberger, who is a PhD student at LMU, Phantom Nam, as well as Robert Zaringer and Benjamin Stein. So here's the the outline of the talk. So I will first motivate a bit what we look at. Then I will present the mathematical model and the results. Then I will try to explain the strategy. So it's something many of you heard many times already. So what the Bogoliubov strategy is and how do we correct it, right? So the Bogoliubov strategy is the quadratic approximation. And of course, this does not yield results which are accurate to any order, and we need to correct it, which is often referred to as the Landau's correction. So here's the physical motivation. So we are looking at the dilute Bose gas, and this picture you've seen it many times, and I'm legally obliged to show it to you. So here you can see a very cooled, very cold Bose gas that transits to BEC, and you can see that when the temperature decreases, then there's an accumulation in momenta. So this is a map in momenta. There's an accumulation at one particular momenta, so most particles occupy the same macroscopic state. So I will not tell you everything that you already know, but this was predicted, well, 100 years ago, actually, by Bose and Einstein for ideal gases. And the challenge is to extend it or to see what happens when you tune up the interaction. It was observed in 1995, and if you want, you can, for what we will study, you can look at this as the first order of the theory, namely that most particles are in a condensate, and then to see something interesting, you want to look, or you want to describe the excitations beyond. Right, so to finish, you should think, I mean, the condensate, as you already all know, is you want to look at it as all the particles or most of the particles being in the one body or one one particular orbital. So the many-body wave function sort of factorizes in this way. And then there's the next order of the theory, which here is represented by the physical phenomenon that corresponds to superfluidity. So it's a big word. And you can think of it as the second order of the theory. And it was in some way predicted by London, because London thought, okay, so helium-4 are bosons, and there's a phase transition, so it must be linked to Bose-Einstein condensation. But then this was, Landau was the first to give a heuristic or phenomenologic heuristic explanation, which was then derived by Bogoliubov. And this explanation concerns the excitation spectrum of the particles on top of the Bose-Einstein condensate. And Landau's explanation, as I will explain to you, relies on the fact that the excitation spectrum of those particles behaves linearly at small momenta. Right, so the excitation spectrum of the system is the amount of energy it gains if you exchange some momentum p. So that's this relation. Sorry, it's a bit at the bottom. I don't know if you can all see. So, is this no? Okay, so what is Landau's criteria? So assume that you are in your BEC and you are in the frame, you are in the reference frame of your BEC, so your Bose-Einstein condensate do not move, and you have an incoming particle at momentum p. If you believe in the law of physics, then there's conservation of energy. So, sorry, the particle has a momentum v. So before collision, the kinetic energy of the system is just the kinetic energy of the particle. And after exchange of momentum, well, it becomes this, right? So the particle lost momentum p, so it has momentum v minus p, and its kinetic energy is 1/2 of v minus p square. And the kinetic energy of the gas, because it has absorbed the momentum p, becomes E of p. Oh. And then you simplify this equation, right? So I just expanded and simplified. And then if I divide by p, and if this quantity is positive, so the minimum of E of p divided by p is non-zero, then this defines a minimal momentum below which the previous equation cannot have any solution. So I cannot have exchange of, and that was Landau's explanation for superfluidity. And then this criterion was later derived microscopically by Bogoliubov, and this is upon what relies statistics strategy. Very good. What else do I want to say? Let's go to the more mathematical content of it. So we are looking at this Hamiltonian, so it's a many-body Hamiltonian. We look at n bosons. So they have a kinetic energy represented by this term, and they interact through a potential V. Bosons means that the space on which this Hamiltonian acts is the space of n copies of L2, and it's the symmetric tensor product of n copies of L2. So that means that my many wave functions, like, it's invariant under exchange of its coordinates. And the assumptions of the potential are pretty simple. So in particular, I assume that V is repulsive, so non-negative, radial, and compactly supported, even though this is not really so important. It just has to be short range. And one of the parameters of the system I want to study is just the density. So it's the number of particles divided by the volume. So I didn't tell you, but I had volume. So L cube, and I will let L go T as well as N, and having rho the density fixed. So this is known as the thermodynamic. Yeah, that's a good point. So here, because we look at the thermodynamic limit, boundary conditions don't matter. So the limit of the energy will not depend on the boundary conditions. The ideally periodic, whatever you prefer. So the first order will not depend on the boundary conditions. And there are two types of questions we would like to address, namely the description of the bottom of the spectrum of Hn at low density, so n is large, as I told you, and rho is small. So we can actually fix L, right? It will be even easier. But we just need essentially that rho is much smaller than 1. And of course, you want to describe the spectrum, but also its eigenvectors. And the big thing is to prove Bose-Einstein condensation. So namely that you would like to prove that a macroscopic a number of the particles remain in the same one-body quantum state, which is essentially summed up by this formula. And this is still open, and this is one of the main challenges of the works concerning this Hamiltonian. But we can say something about the bottom of the spectrum, and this is what I will talk about. Are there any questions? Is the setting clear? Yeah, thanks. So this is the Dirac bracket notation. So it doesn't have to be one, but you would like that one macroscopic, one specific orbital is macroscopically occupied, and here one is just the first eigenvalue of the free Hamiltonian. So if you take periodic, it's going to be 1. It's true that it's in a boundary case. But even if it's not, if you take Dirichlet, then nevertheless, you can do this computation and you will get something sensible. Please. Yeah, so this is the expectation of this operator against psi naught. Psi naught is the ground state of the system, and here this is the orthogonal projector onto the constant function. So here that's the orthogonal projector acting on the ith variable. Okay. So let me tell you about, so here we have dilute systems. And for dilute systems, we expect that to leading order, two-body collisions will lead to events. Right? So if you just think of the two-body problem in relative coordinates, you end up with this energy. So here I took, in a way, Neumann boundary conditions. And if I minimize this energy, I obtain a quantity which is denoted by 8 pi a, and a is referred to as the scattering length. And so this 8 pi a is also referred to as the scattering energy by extension. And it is true that most of the energy to leading order comes from two-body collisions. And we have this energy expansion. So in the dilute limit, rho, so you can take A to be fixed if you prefer, but you can also vary the potential. But in the dilute limit, so rho A cube much smaller than 1, the leading order to the energy per particle or per unit volume, it's the same, is given by two-body collision. So this 4 pi rho A. And you can think of A, if you want, as an effective range of your interaction. So in particular, if you take V to be the hard core at radius A, then you get the same A. So this was proved. I mean, an upper bound for this inequality was proven quite soon by Dyson, and he also told us, okay, how to think of the low energy states of the system. So in particular, he used the following trial state. So he, not exactly, but it's in the same flavor. This is called the Jastrow factor. And it's just the easiest way to encode two-body correlations. You take F to be the solution of the scattering problem. So it's going to be to solve an equation minus Laplacian F equals minus 1/2 of the F. And you just take the product of F of xj minus xk for all j and k, and you plug it in, and you can compute with a bit of effort this quantity here. The lower bound was a bit more complicated. It was proven 30 years later, no, 40 years later by Lieb and Universal, and that relied on essentially two ingredients. One which was named the Dyson lemma in reference to the work of Dyson, and well, the temporal inequality, which is just the perturbative ingredient of the proof. So the Dyson lemma tells you the following, that you can replace V, so V is the interaction potential, by paying, I mean, the price is the kinetic energy. You can replace it by a potential which has a much larger range. So it has branch R, but it integrates to, I mean, U is anything you want, actually. The characteristic function of this. And I didn't write it, but the integral of all of this is just 8 by 8. So the Dyson lemma is a way to say, okay, it's a way to de-entangle these two, this minus Laplacian plus V. And by using, I mean, sorry, by by estimating from below, by a potential which is smoother and whose integral is exactly this scattering energy. And then the second ingredient was the temporal inequality. Let me not comment too much on that. So, in fact, just before Dyson's article, where he proved the upper bound, in the same journal, in the same issue, actually, there was a paper from Li Wongyang where they computed non-rigorously, of course, the next order to this expansion. So E naught here is just the infimum of the spectrum of Hn. And they do this dilute limit, so rho small. And they compute the next order, which is this ugly factor here. And like this, it does not talk too much, but it actually you actually understand something if you look at the excitation spectrum that they predict. So E naught is this the ground state energy, and they tell you that the excitation spectrum of your system is of this form. So I will first tell you how you should read this. So what they tell you is that your system to second order is unitarily equivalent in some way, in some sense, to a system of independent quantum oscillators. And they give you the dispersion law. Right, so MK are integers that you can choose however you want. And K is the momentum. It's in the dual lattice your box. Absolutely, yeah. So to my defense, I just copied it from the article. But I think it's in physics articles. If you write the bold font, it's a vector, and otherwise it's the absolute value. And you can see that here, so it has this peculiar form that features this rho A. So if you take A to be 0, you just have dispersion. And now, if you tune the potential, so A will be positive. And well, you can see that it fits, it satisfies downward criterion for superfluidity. So in particular, this guy is linear at small k. Yes? Yeah, it's a good point. I forgot. Ah, of the same authors. Yeah, yeah. So I think they had like how to say how is it called? When you say that you got an announcement, yeah. Yeah. Because I think in the first paper there was only Li and Yang, right? There were only first two of the authors. Thanks. Okay. What else did I want to say? Yes. So essentially, for K small, this guy is linear. So it's linear with coefficient square root of 16 pi a rho. And for K large, this thing is just quadratic. So you recover the quadratic dispersion relation. And that also tells you something else, which is the typical momenta, the typical order of momentum in your system. Right? So it becomes linear, and then it becomes quadratic, and it becomes quadratic when those two guys equate. So when k is proportional to square root rho a. Right? So that tells you that most of your excitations in your system are proportional to, I mean, their momentum is proportional to square root rho a. Okay, so that gives you like a characteristic length of your system. Okay, so now we were interested in deriving so the first formula was derived by Yao Yin, and then later the lower bound by Seren and Jan Philippe. And we were interested in like justifying the next formula about the excitation spectrum. So now if you have a closer look, you would like to prove that the next eigenvalue or the next eigenvalues are of the form E naught plus quantities of this form. But P is in the dual lattice of the box, which is very large. So if you take P small, I mean P of order 1 divided by L minus 1, divided by L, this whole thing is of the order L to the minus 2. So you will never be able to see, I mean, except if you are very, very good, maybe, the next eigenvalue of your system or the few next. So you have to rely on something else. No. So what I meant, what I meant is that so I meant that if you look at the current state energy, so E naught, if you divide by the volume or n, the limit does not depend on the boundary condition. But of course, the spectrum does depend on the boundary condition. Absolutely right. So you're totally correct that I mean, if you want to relook at the next eigenvalues, they really will depend on the boundary conditions. Yeah. Well, you should ask Li, Wang, and Yang. So I mean, in the end, the lattice becomes R3, right? Because the spacing of the lattice becomes very small, so it should not really depend on the boundary condition. But of course, if you yeah, exactly, right. So I mean, there will never be really one excitation. I mean, it's physics, right? So they don't care about boundary condition. They should maybe, but yeah. So I hope this. Where am I? Okay. So instead of looking at each separate eigenvalues, we look at the free energy of the system. Yeah, that's a good. So here, I mean, because this 2 pi z cube, I chose implicitly the periodic boundary conditions. Periodic. Yeah. But of course, you can choose whatever you want, and you can ask the same question. Yeah. But then instead of having a z cube or 2 pi z cube, you'll have pi times n. And so instead of looking at each specific each eigenvalue separately, we look at the free energy of the system. So we call it F and T, and so T is the temperature of your system. And it has this formula, right? But so it's minus T log trace of E to the minus Hn divided by T. I'm sure you all saw it. And I teach you nothing when I tell you that this is obtained by minimizing the free energy, I mean this free energy, and which this is called the Gibbs variational principle. No, this is a typo. So yeah, so there should be only one logarithm. So this is trace of gamma log gamma. Yeah, so that's the regular entropy. Sorry about that. And you minimize it over density matrices, which are positive positive states of trace one. Okay, and that's the result. And then so we take V to be non-negative, L2, and those are technical assumptions, radial compactly supported and non-increasing. And then we are able to do the same thing as we did for uh, the ground state energy per unit volume, but for the free energy, right? So here, this free energy at temperature T, you can look at it as an average of eigenvalues of with at order T, or less. And what we say is that we recover the formula of Li Wongyang to the two first order of the formula, and a thermal term, which is nothing but what you expect. So I told you, I claim that Li Wongyang pretend that the system is, in some sense, unitarily equivalent to an identical, to independent quantum oscillators with this dispersion relation. So here I just plug, I just replaced Hn by this guy. So here B dagger and B are the bosonic creation and annihilation operators. And I just plug this quantity here, and I corrected it by the energy. And you can, so for large L, this sum becomes an integral. So you can compute it. I mean, you can just approximate it. And you can do a change of variable. So you can put the T on in front of the integral. And you see the following, namely that when T is of order of rho A, so if you remember rho A, I mean like square root rho A, sorry, was the typical size of the momenta in your system. And when T is of order square root rho A, is of order rho A, then the thermal contribution becomes of the order of the Li-Wongyang term, so the correction to the leading order. And also when T is of order rho A, if you look at the dispersion relation, then there is actually a contribution coming from the interaction, because this term over there is of order 1. And this is the regime that we can cover. Actually, we can do a bit better. We can go to rho A times a negative power of rho. But and I wanted to say something. I forgot. Yes. So this also gives you a new interpretation of this second order correction. So the Li-Wongyang term, right? So the Li-Wongyang term, what is it? It is the ground state energy, the renormalized ground state energy of this sequence of quantum oscillators. But if you look at x square, minus square, you can write it A dagger by naming A B X enable it is, and then you pay this 1/2 here is this quantity. So it's really a picture that that goes together. Very good. Are there any questions about the result? Very good. So let me tell you about the book. Yes. I think they do this pseudo potential technique. I don't know. I just gave up. I don't know if it's a value. But yeah, exactly. Once you can, yeah, I mean, once you renormalize the potential, I think this is what is pseudo potential these guys. Sorry, what? No, they replace the hardcore by what is it? D over x times r times a, and then they just run all the computations for this. There might be a parenthesis mistake. Where And okay, so this is the result of three works essentially. So I've got to tell you. So we first derived the lower bound with those people, so Haberberger, Heinzelnam, and Saringer, for L1 potentials, and it was later extended with Seren and the Copernican gang, as we like to call it, for hardcore potentials. So a hardcore potential is when you take I mean, you know what the hardcore potential is? You have T outside of the pole of radius A. It's very unnatural. And then what I want to talk about is this, in particular, the upper bound that we get with Florian Haberberger, Christian Heinzel, and Benjamin Stein. And this holds for L2 potential. I have 20 minutes. Up, very good. So let me tell you about what Bogolubov did, so the Bogolubov approximation. And I already told you it's a quadratic approximation. So you write your Hamiltonian in a second quantized form. So here I took periodic boundary conditions. And so you get this, right? We can check that there is conservation of momentum. So if you have two incoming particles, one with momentum P and one Q plus R, then the two others have momentum P plus R and Q. So this guy preserves the momentum. And that's inherent to periodic boundary conditions. Up. So what Bogolubov does is that it says, okay, the zero mode, so I assume I have pronunciation, the zero mode is macroscopically occupied. So I can replace this quantum number by a classical number, namely the expectation of this guy on the state. And since most of the particles are in the coordinate state, then I can just replace it by square root n. Then this breaks the conservation of particles of this Hamiltonian. So I have many terms. So I replace some the A0 and the A dagger 0 by square root n. I obtain many terms, and I just do a quadratic approximation. So I truncate and only retain the quadratic guys and what's before. So there's one guy where all of the A and A daggers are indexed by 0, and that gives me V hat of 0 times n rho divided by 2. So that's my leading order. And then I have this guy over there. And this is a very nice Hamiltonian because it's quadratic, and we know how to diagonalize quadratic Hamiltonians. How to do so? Well, you just do what is called a Bogolubov rotation. So you denote by P, a linear combination of, I mean, it works for this particular case, but there's a more general theory. A linear combination of A dagger P, and here it should be A minus P. Sorry for the typo. Those guys, if you chose wisely, alpha and beta, they satisfy the CCR. And you can complete the square, exactly as in the case minus Laplacian square. And you get some operator which is quadratic, so diagonal quadratic. And the price to pay off is this constant energy EBOG, which is written here. So you see, as I promised, it's really related to the dispersion relation of it. And Very good. So you can, this was just a side comment. Yeah, so here it's very nice because quadratic Hamiltonians, they belong to, I mean, they are described by an exact theory. So you can diagonalize them exactly by some unitary operators which are called Bogoliubov rotations, and they are just exponentials of quadratic Hamiltonians, to simplify. Okay, so is this the end of the story? Absolutely. Yeah, absolutely. Well, it is, you will see later, but it is implicitly what Bogoliubov does, right? By doing this thing. Yeah. No, no. Sorry? Ah, what do you mean? Yeah, yeah. I mean, this is, I'm just telling you what Bogoliubov did. I mean, what was the intuition. And then Bogoliubov did not talk about unitary transformations or anything. I'm just telling you as a side comment that this is nice because, I mean, quadratic Hamiltonians are nice because you can diagonalize them. So, yeah, please. No, so yes and no. I'm cheating here. But so if you restrict it to the n particle sector, you obtain exactly the Hamiltonian from before. Now, of course, here, why am I cheating? Because you see that if you test on a n-body state, you will not see those guys, the off-diagonal terms. So here I'm implicitly using the equivalence of ensemble. So I'm looking at a Fock space, the canonical setting, and this was just a sort of a hand-waving explanation. I mean, so if it preserves the number of particles, it also acts on on a specific particle number sector. You see here, I kill two particles and I create two other particles. So this guy is a well-defined operator on Hn. Yes. Yeah, yeah. So here it's an approximation in some sense. Maybe we can discuss later. I'm happy to. Seren, you had another question? Mhm. So uh, I did not understand the comment. Mhm. Absolutely. Yeah. But here, I mean, so I did not write A0, A0, right? So I just assume that I am on the Fock space, on the canonical setting, and I just cheat shamelessly. No, I just replaced it. Absolutely. I mean, I just take it as an ansatz if you want on my canonical setting. Okay, so commercial break. So if you believe this is correct, then if you want to derive an upper bound, you might think that, well, it's enough to look at test and quasi-free states. And quasi-free states are states, so I don't know how you call them, homogeneous quasi, no, are states that satisfy the Wick theorem. And Well, since it's Volker's birthday, I have to say that at least in the family case, I uh, I learned quasi-free states by mostly with your article with Lib and Solovech on the generalized hard-clock theory, and then later I did with the bosonic case. No, Mathieu was my boss. So I think this was the base for Jan Philip's lecture notes later, right? At least partly. Uh, yeah, yeah. I've heard that. So anyway, so quasi-free states, they have this nice property that you can compute the expectation of any product of creation and annihilation only knowing their two-body correlation functions. So that is what you obtain if you test on A dagger A or just A dagger A dagger. And by doing so, we can compute, we can have a pretty good estimate on the energy. This is what Erdős-Schlein and Yao did. And they tested, so they took the Hamiltonian on the ground canonical space, on the Fock space, ground canonical ensemble. They first did this Weil transformation. So they introduced condensate with density square root and node. And then they took a quadratic, they did a Bogoliubov rotation of the vacuum. So of this form. So as I told you, it's the exponential of a quadratic Hamiltonian. And here, CK, it's a correlation function. It's essentially, it encodes, or it's very well connected to the scattering solution. So this F that we saw before, appearing in the Jastrow factor. And C is chosen so that it's L2 norm. I mean, it creates n minus n naught particles, where n naught is the number of particles in the condensate. And well, they found they computed this upper bound. Right? So they recovered the leading order to the energy, which was sort of better than what you would have expected before, because before you only had the p hat of 0, so the integral of p appearing. So for hardcore, this is very wrong, because the hardcore is not L1. And they obtained a second order, which was of the right order, but with the wrong constant. So ESY is for Erdős-Schlein. And nevertheless, in some weak limits, so for soft potentials of this form, they could recover the Li-Wang-Yang correction, but not in a general case. Okay, so this picture tells you that, well, you have to go beyond beyond the quadratic exponentials, and that it's not enough to test on quasi-free state. And this step, or this renormalization process, is often called Landau's correction. So what to do to be able to reduce the system, reduce the problem to quadratic exponentials, quadratic tri-state. So this is the formula that we got from the quadratic approximation. Right, so that's the leading order. And this was the sum that became an integral, if you remember. And what Landau told Bogoliubov is that p hat of 0 is not a physical parameter, and it will be replaced by 8 by A, scattering energy that we saw at the beginning. And if you do this, then of course you get the correct leading order. But then if you look at the integral, it does not converge anymore, which is inconvenient. So if you do the Taylor expansion, the next order you get is proportional to 1 over p squared. Okay. And well, if you just subtract it, because if you believe physics is coherent, you obtain a converging quantity, which now you can compute, and that gives you the Li-Wang-Yang correction. And to understand what is happening, we have this interpretation. So, sorry, Bogoliubov approximation only retains a particular type of regions, which we call we call hard collisions, and they only involve two particles outside of the condensate that becomes two particles in the condensate. Right? And this is what you get if you only restrict yourself to quadratic states. And to get the next order, you should not neglect what are called soft collisions. So namely this term, this cubic term. That involves collisions where two particles outside of the condensate collide. One goes in the condensate and one stays at low momentum. So this is what is meant by the index of the sun. So actually, you can restrict to two high momenta particles that become one at low momenta and one. So it's almost like before, except that you allow one of them to be not exactly in the condensate, but close to the condensate. And of course, the characteristic length of the system is this square root rho A, so the typical size of momenta of your excitations. Okay, so the first to obtain the correct upper bound were Yao and Yin. And it's an article which is a bit complicated, and I never understood what they did. So they took a trial state, they just constructed a trial state implicitly. So I mean, I could not understand what they did. The next reference I would like to mention is Bocato-Breneke-Chenate-Punchline. So they managed to essentially adapt the Bogoliubov rotation strategy, but for the cubic correlations. So they managed to expand this exponential of a cubic kernel, which in a way you should think of as your Jastrow factor. So CR is essentially the Fourier transform of F. And using the GML formula, they managed to find almost exact relations as in the Bogoliubov rotation case. And because it's a unitary transformation, they managed to compute the excitation case, the excitation spectrum in the Gross-Pitievsky case. So where the size of the box L is proportional to N, so it's an ultra dilute regime. So it's much easier in a way. Computations are much easier than in the thermodynamic case. Okay, so blah blah blah. Maybe in 2 minutes. Oh, sorry, I will just flash this slide. The usual strategy now is to use Dirichlet bracketing. So if you say a thermodynamic limit, then the typical methods rely upon dividing your systems into subsystems and do Dirichlet alignment bracketing. And for an upper bound, you do Dirichlet bracketing. So we divide systems, we divide the big thermodynamic box into fixed boxes where the size depends on the density. I will not say more about it. And because it's in the box, the system is much more dilute, a bit like in the Gross-Pitievsky regime. It's much easier to run computations. So, however, if you want to do an upper bound, you have to work with Dirichlet boundary conditions, and you have to take boxes which are very large. And for very large boxes, well, the interaction in the system is not so dilute, and the interaction is you're not in the perturbative regime. So let me just touch this. What I want to say is that you cannot use the strategies from before and expand via the GML, because the kernel you expand with is not small at the low energy states. So the GML expansion is not converging anymore. So what Bastich-Chenate-Punchline did is a non-unitary transformation, right? So they looked at a kernel of this form, and because they only looked at the ground state energy, so they recovered the Yao-Yin result with the method from before. And they only test on the vacuum, which in a way allow them to run computations. and blah blah. I just want to say the result. And I'm done. If you want to recover the excitation spectrum, you cannot only test on the vacuum, you have to test on the Gibbs state. So we really had to create a cubic transform, I mean a unitary cubic transform, and to obtain exact relations. And this we did using ideas from this paper, Bastide-Schneider-Einstein. And so we have a cubic transformation which features exact closed formulas that allows us to run the computations and to do Landau's correction. And okay, I don't want to go into the technical details. I will just stop here.
Thank you very much for this very nice talk. I suppose there's plenty of questions.
So my first question is, I come back to this again. When you look at all possible Bogoliubov transformations, so all let's say linear transformations on the creation and annihilation operators, then nothing prevents you from choosing an inhomogeneity for non-zero momentum. And also you could mix the zero momentum with the non-zero momenta. And but this apparently is not the case. So and couldn't that not be the reason that the quadratic approximation is not good enough? No.
So where am I? So well, so here this is what they do actually, right? No, this is. So here you see, I mean, I did because I wanted just to claim that those are the quasi-free states. But actually, if you put the Weyl transform there, is it exactly what you're saying, right? That you also have non-zero expectation on linear terms. So you mean that you can also have non-zero expectation on linear terms? This is what you mean? Or? Okay, I don't understand.
Single, I mean, on the expectation values of a single creation operator with non-zero moment.
Yeah.
So the Bogoliubov replacement,
yeah.
There's.
Yeah. So here, at least in the periodic case, you don't have any terms of this form because of conservation of momentum. So here, if this one is 0, 0, 0, the fourth time is also 0. Okay, maybe we can discuss it. Sorry for not understanding.
Are there further questions online?
Well, when dealing with the Bogoliubov transformations, there appears the issue of implementing them in the original Hilbert space.
Absolutely.
And is that an issue here, or?
So this issue was taken care of in the paper of Bocato, Bonnecke, Schneider-Einstein, when they did it in the Gross-Petevsky regime. And this is actually a very lengthy computation. So what you can do instead is to follow the C-number substitution, I mean the rigorous version of the C-number substitution introduced by the article of Mathieu, Nam, Sarfati, and Solovej, which embeds the n-body space into a truncated Fock space of excitations. And now this, I mean, if you extend your Hamiltonian, which is on this truncated Fock space on the full Fock space, there you can do your computations with exact formulas. And this is also what we did in the Gross-Petevsky regime with Nam, and later with Benjamin Stein and Christian Heinze. So we sort of simplified the approach in their paper by doing this. So we look at the truncated Fock space over the excitation, which is isometric to the n-body space. And then we extend it to the full Fock space to be able to run computations. But for the cubic, there's no, it's not exact.
Thank you.
Sure.
Thank you. Can you maybe go back to the last slide? There was something about some exact formulas. What did you mean by that?
Okay, so thanks for the question. So, so we have to exponentiate the cubic term. Okay, and instead of exponentiating this double sum, put it simply, so there's a fermionic interpretation of those soft pairs involved in those soft collisions. And in this article of Bastide-Punchline, they use this cutoff that essentially implement a Fermi Pauli principle, sorry, saying that those pairs they act like fermions, not because of antisymmetry, but because of exclusion principle. So if you have a pair of high momenta excitations, so here it's minus R and R, and if their sum is equal to P, so we call them a P connection. So this was our interpretation. I mean, this is also their interpretation. And they say, Bastide-Punchline, that they can only be one P connection, one pair that adds up to P. And then essentially what we do is that we take this interpretation seriously, and we create this B-layer P that creates this soft pair and kill one low momenta particle. And because it's fermionic, then you square it, it's equal to 0. And now, I mean, you can just compute the exponential at fixed P. So that gives you a cos, a sine, which is reminiscent to the fermionic case. And this guy XP, this is just modulus square of BP, and BP is small in the regime we consider, and then you can expand. Of course, this is for one P, so you have to read for all P's. So you have an infinite number, I mean, an increasing number of unitaries, but because of rules that we set, we can compute the expectation of the Gibbs state after doing this transformation. Sure. Thanks for the question.
I have two kind of more what's the word, metaphysical questions. So the one is, why not grand canonical? So why are you working with the density as a parameter? And the second question is, I mean, you had these results with B in L1 and hardcore and B in L2. What's the motivation for these different choices of potential? Is there a certain model that a physical model, I mean, in reality, that you want to treat, or maybe you can comment?
Absolutely. So for the first question, why do we not work canonically? So we do work canonically actually. So for the upper bound, we do work canonically. That does not rule out the problem with the cubic renormalization. But at least for the quadratic ones, there's not this problem of having to construct rotations, Pogolubov rotations in the n particle sector. Why they had to do that before is that they were looking at the Gross-Pitevsky regime, which is a dilute regime, and for which you don't have equivalence of ensemble. So if you don't have equivalence of ensemble, it's important to work on the canonical setting, because for your second question, I mean, does that answer your first question? Or? All right. And the second question was about why do we care about hardcore? So physicists say we consider hardcore because it's easier, but for mathematicians it's much harder. Maybe a better answer is because it's important that I mean, it's a natural question to know if the terms appearing in your expansion only involve only depend of one parameter, which is the scattering length, or if they depend of the detail of the potential. Because in experiments, people, they don't know the potential that connect the particles, and they just want to measure everything in terms of one parameter. And if you talk to, I talked to a physicist recently, so it's not a rule, it's only for one physicist. And she told me, we don't know what the scattering length is. So they have one parameter and they just do everything with it. And it's important to know that everything only depends on one parameter and not on the detail of the interaction.
Expect things to simplify a lot. Any
Yeah.
any hope that this would lead anywhere at any density?
So the thing is, for larger densities, where is the? Oh, no. Right. So for larger density, then you don't see this guy anymore. However, if you know what happens at a higher density, so you have this phase transition. So particles, they go out of the condensate. And then there's also like this an exchange effect that also changed the leading order. And in fact, you could also see it if you just formally expand here for large T. So this formula should hold in a way for larger T, even though this contribution becomes negligible. So here you only have the the energy of the ideal gas.
Further questions? Online, maybe? Or maybe I have a silly question, actually. So on your first slide, you showed us this picture that we have seen sometimes already.
Yeah.
And I was wondering, now you have an asymptotic expansion, and well, if you have an energetic expansion, then sometimes this can be used to say something about the density, not necessarily in X, but also in P space. Do you think you can reproduce this kind of image mathematically? To say something about the one particle density, let's say, or
the one particle density should be close to the orthogonal. So the conjecture is that it's close to the. Yeah.
Yes, but can you in the limit, and can you make
Yes,
any statements about other length scales, or?
Yeah, so there's a conjecture for the number of particles outside of the condensate. So if you look at those articles, and the fraction of particles outside of the condensate at 0 temperature is smaller than square root of rho a cubed. So it's in the Ludwig-Maximilians paper, actually. But then the conjecture is that the one body density matrix approximates this. The next order, I guess, this should be given by the Bogoliubov approximation.
So
you have the Minfield and Pospetevsky works on that. By Nam, I think Andreas Deutschert, and I don't want to, maybe Marcin Apolkowski.
Okay, thank you very much. Now I think that's it. So let us thank Arnaud and all the speakers of today's session again.